Okay, we can start with this tutorial, which is actually a kind of follow-up of the previous, so about HCI and users and graphs, basically. So I'm Davide Mottin, and I'm co-presenting this tutorial with Emanuel Müller. We are both from the Hasso-Plattner Institute. This is one of the pictures of the Hasso-Plattner Institute. And this tutorial is about a very promising ground of research. As we heard before, actually there are several challenges. Somehow, when you have to deal with user, you have to consider a large amount of different things. So it's not that you are just showing to the user results. You're not just providing services to the user. You have to somehow have a dialogue with the user, and this is a very important part. So let's start. Okay. Yeah, of course I don't have the pointer. This is us, and basically I'm a postdoctoral researcher in the group that is led by Emanuel, and this is the site of the slides. You can find the shorter version, but also the larger version that we presented in CIKM last year. If you Google HPI graph exploration tutorial, you will end up in the page that is the sister of this page, basically. Okay, so so far so good. Let's start with the vision. So, well, we are all talking about this big data. So we are here, we are in a database conferences, big data are everywhere. They are complex for us that are a researcher in this area. But for a normal user, this big data problem is really huge. So they don't even realize that they are producing data every single time, every single second. So you come here and your smartphone is sending data. Then we have sensors around. We have your cars that collect data. So data are really everywhere. And this interesting thing is that basically, if you put the user in this picture, you see that the user is completely lost. So the user looks at this data, doesn't understand anything. But I'm not talking about expert user as us. I'm talking about normal users. Even though for them it might be playful, it might be nice to play with the data. We can have even more data expert if we have tools and algorithms that support this vision. Luckily, Stratos Idreos presented actually a tutorial a couple of years ago in SIGMOD, and he presented what is called data exploration. It's not a new concept. Data exploration is about finding or sending exploratory queries to a bunch of data in order to retrieve information, even though you don't know what you're looking for. So the amazing thing with data exploration is that you have the so-called exploratory queries that are queries that might be imprecise, that might be very generic, but still you can get inside of the data. So even a user which is, okay, maybe not a novice user, but somehow a user that doesn't know exactly how to crawl the data, all the data mining processes, all the database processes, can somehow have a better look on the data like this and say, okay, we have statistics, so we can project on a map. Like here, it might be the crime rates, for instance, or something better, I don't know, the consumptions of some sugar or cake, and we can immediately understand. So we have created a bunch of these techniques. Visualization techniques, but in general, analytic techniques. And well, we are experts, and we have experts also that can tell us what is going on. But also the user, which is not a very, very expert user, can somehow have a vision, can somehow have a glimpse on this data. Well, so far so good. We have seen many of this research going on with normal data, but today I want to talk about graphs. So we already talked, the previous tutorial already stressed this fact that going into graphs, searching into graphs is hard. And it's hard if you have a user that is looking to this data, because it's a very nice model, it's a very simple model in which you have nodes that are connected through relationships. It's very expressive. So it's not many data can be represented as a graph. Almost everything. And the relationship will give you extra information. This extra information comes directly from the idea of propagation of information, of some semantic relation. So when I buy something, then I create a link, a purchase link. When I do something online, when I search something online, I create a link on this page. I'm connected through my friends. I think many of you have a Facebook account or a Twitter account. So social networks are one of the perspectives, but we also have recommendation graphs. We have knowledge graphs that are actually graphs in which the nodes are entities and the links between the nodes are relationships. So like Donald Trump is the president of the United States and this president of is the relationship. And we have that road network. So this has been studied for a long time. Problems here are like, I search for the shortest path to go from here to there. But in the world of smart cities or in the nowadays world, it's not just going there quickly. We want to go there because we like some of the shops on the way. We like some of the attraction. We are attracted from art. So it's richer, the world now. And the idea is that we have complex, ubiquitous. So these networks have attributes, have directions, have weights, have probabilities, have everything inside. And they are really large. So even if you consider yourself and your network, and just today you are connecting with many people, you are connecting through your laptops. You are connecting in many different ways. So if you consider all the kind of relationships just today are tons of them. And they're variable. So you can extract not only, well, we are interested in the knowledge from the graphs, but of course there are companies that are making money out of this knowledge. So let us consider that talking about graphs is not just a side effect. So, however, now look at the vision or look at the user perspective. The user is somehow aware, so I can consider myself, I'm connected with my friends, and from this connection I know pretty much what is going on. I can somehow have a vision in which I know the friends of the friends, so I basically know what is going on with other people that are maybe connected with my friends. Maybe they are going out for an event, for a concert, so I can know this kind of things. However, this is really a tiny picture. It's a tiny picture in a huge world. And this is not even huge. This is a visualization software. Right now, visualization software can produce this kind of visualization. We have seen before that we are studying better ways to visualize this data. But right now, many softwares will produce such a picture, which is kind of useless, I would say. So it's hard to find out useful information from there. So okay, we are lost. Well, we hope not. So in this tutorial, I really want to convince you that we are not lost. We are studying these problems. We just don't realize how important this problem is. And I would like to challenge you in studying this problem even further, because this is very important. Okay, so the current view, as I said, is visualization tools. I will not talk about visualization tools. I will talk about algorithms in this tutorial, but let's have a look, because the algorithms will support these visualization tools. So we have many visualization tools. They are somehow complex to use because you have to know what modularity is, what in degree of a node is, so very complex ideas behind. They don't scale very well. So try Gephi, and if you have already 100,000 nodes, well, things become hairy in a normal machine like this. So there are, of course, there are other things that have been studied, like partitioning or large-scale graph analytics, but are really for expert users. So they have somehow limited expressivity. On the other hand, from the database perspective, we are used to query languages. Query languages are amazing tools. Declarative languages have been studied for decades. And for relational databases are really useful, but it's my personal view to say that for graphs, actually, these languages are pretty cumbersome. Just because when you search something in a graph, you need to express a structure. You need to express something more. It's not, and first of all, a very important thing, you don't know the schema of a graph. So when you cast a query in a relational database, you have in mind the schema, and you know what you're looking for. But in the graph, not exactly. You hope to find something, but it's not really true. Anyhow, for any normal user that is using this kind of queries, is actually lost, basically. So there is no interactivity, no guidance. So all the graph query databases are designed for maybe performance reasons, but actually they're very, very cumbersome to use. Okay, I want to just let you know what is this tutorial about and what is not. So first of all, this tutorial is about algorithms. So basically, I will survey a set of algorithms that have been designed for the purpose of helping the user, even though they don't realize that the user was in the loop. It's about approximations. So I think recently there has been also an article talking about approximate queries, whether they are dead or not, from SIGMOD blog, I think 2 or 3 days ago. Well, we can say yes and no, but still I think it is an important aspect. The user is not always so precise in query formulation. It's about interactive methods, so the interactivity also plays a role. And it's about discovery portions of the graphs that are important. So if you look at the graph, sometimes, since it is big and you have seen that the visualization might fail, you can somehow focus on one part that you think it's an important part. But the user is not willing to provide you weight most of the time. It's not willing to say, yeah, this is important 7 and the other is important 8. Not really. Well, the previous tutorial was always mostly towards visualization. In this tutorial, we will focus on algorithms that can support visualization, but don't talk about visualization explicitly. We will not touch query languages in general. We will not have efficient indexes, so there are a plethora of efficient indexes that have been created for graphs explicitly. But this is not the focus of this tutorial. I will talk about techniques that actually answer the queries, and then on top of that, you can construct the efficient indexes. Some of these techniques have indexes, but still, this is not the main purpose. And although it's very interesting, I will not touch the machine learning aspect. Why? Well, because it's still very young, what you can do with machine learning in terms of query over graphs. And second, it requires yet another tutorial probably for this. Okay, so in our effort to understand what was going on in the research, we identified 3 different blocks. So first, it's exploratory graph analysis or analytics. Second is focused graph mining. And third is refinement of query results. For each of them, we will provide the techniques, basically. So let me show you what we mean for these 3 blocks. Okay. Exploratory graph analysis is about exploration, exploratory queries. The user has in mind something, has in mind an information need. And this information need might be imprecise or somehow being an example. So these are the 2 exploratory options that we have found so far in the literature. Well, this is what we have found. So an imprecise query, also called approximate query or similarity queries, in which basically the user is looking for Angela Merkel, which is the Chancellor of Germany, but for some reason he thought, or she thought, that the Merkel is the President of Germany. And this query is imprecise. So if you go into the database, well, any precise query will return a 0 answer, but you can go in an approximate way. And you say, well, with some confidence, maybe you meant that thing, so that actually Angela Merkel is the Chancellor of Germany. And second is what is called the by example query. So by example means that basically the users sometimes think about examples. So if you go in a shop to buy some shoes, you might ask, okay, I would like shoes like these. But you don't even know why you like these shoes. It's just because basically you see, well, it's hard to say, they're comfortable, I think they jump pretty well, I don't know. But this is the idea of exploratory queries. So you have an example in mind, and this example actually is matched into the graph, and then you find similar other results. So an example is now a result that you want, but you don't know how to describe the other results. Second is focused graph mining. Focused graph mining refers to the fact that actually we can somehow focus on few nodes and then infer other properties on the other nodes. So for instance, we just select a couple of nodes, a couple of users that we like, and we discover that actually these two users are similar to these other two users because they all like the Chicago Bulls. Well, it's normal, we are in Chicago, it is possible. So we look around, and in the graph we discover automatically this small community of people, which probably in Chicago is not so small. Space restriction methods refer to a large set of methods. We have identified, for instance, one of them is EgoNet analysis. So the EgoNet of a node is the set of nodes that are immediately connected to the node and the connections among them. There has been a lot of studies in this area. If you look at all the work of Faluchos, Leskovec, Hangantong, and that group in Carnegie Mellon, they have done a lot of things here, a lot of studies, because they discovered that actually you can, just looking at the EgoNet, you can infer information in the entire network. So how it is distributed gives you information on the rest of the network. And third, the reweighting. So I just put a preference of an edge, and then I infer that some edges are more important than others, and I exclude all the others. Third of all, it's a refinement of queries. So we have already heard from the previous tutorial that we can somehow, the user might give you a single query, which is very generic, that returns a lot of results in a graph database. In this case, it's a chemical compound that you are searching for. And dealing with generic queries is a huge deal. And having too many results can be solved by reformulation. So I add some extra constraint on the query, and I will return a set of small reformulations. Second is top K results. Instead of returning all the results, I return just the top K that have some good properties. Maybe they represent the entire set of results, so they are able to summarize the rest of the results. And third is skyline queries, in which basically you cast somehow a dominance relation, and you have a multi-objective function that says, okay, I want to have the best relevance, the smaller query, and so on and so forth. And basically you find queries that are not dominated by others. Okay, just for fun, before coming here, I thought, okay, let's compute the co-citation graph of the work that I'm talking today. And basically it turned out that there is a pretty neat click on the work about exploratory graph analytics, But if we look to the focused graph mining, for instance, these are techniques that have been developed in data mining community, which is not far away from us, but for some reason they are not aware of the connections. So maybe we should actually try to think that other communities have interesting things, like HCI. So let's foster collaboration. And this is one of the, this is the main part of this picture. Okay, I will just really quickly go through background. I guess almost all of you are aware of these background concepts, but just to recap. So a graph is usually a tuple, in this case a pair, so you have a set of nodes and a set of edges, which is a set of pairs of nodes. They might be undirected, so no directions on edges, directed, labeled graphs. There might be probabilistic graphs, so in which you have probabilities attached to edges. We have graph databases, so for instance, set of chemical compounds, and which are actually very important and very well studied. One of the most important things you have to keep in mind is that we will talk about variations of graph isomorphism, or better, subgraph isomorphism. So graph isomorphism is the problem of matching two graphs together in a structural way, so you find a bijection among the nodes in the graphs such that the edges are preserved. Subgraph isomorphism is the same problem, but searching substructures, so you search for the structure Q in the graph G. And the last thing is, okay, sorry, because the visualization changed a bit. So graph clustering or partitioning or community detection, well, it depends. So sometimes community detection might be deemed as also as partitioning. Some other times you have overlap among communities. In this case, it's not a proper partitioning, but still, it's actually something that is very important. So every node is assigned to one or more communities. One community is if you are talking about non-overlapping community. If we're talking about overlapping community, this assignment might end up in multiple clusters. And they use a bunch of different quality criteria like modularity, like conductance, mean cut, and so on and so forth. Okay. Let me start with the first part about exploratory graph analysis. Okay, in an exploratory search, as I already said, the user has in mind somehow a query, but this query might be imprecise. If the query is imprecise, then we need a method that is flexible enough to cope with these imprecisions. Second, the user might not have in mind a precise query, so it doesn't know how to describe the objects of interest, but it might have in mind some structure or some example which belongs to the set of the results. These two things are somehow related together, but they offer different perspectives. So again, if you want to build your system, it's useful also to think about these two ways of casting exploratory queries. So in approximate graph search, as I already said, so if you go, for instance, the question here is whether the yellow node on top of the query graph is similar or is close enough to the orange node on top of the graph. And there are a set of solutions. Some comes from neighbor areas, some other comes from our, from the database community. We will survey them anyhow. Okay, so what is the issue with subgraph isomorphism? Subgraph isomorphism is too strict. There is no other way. So you have to find exactly the same labels and exactly the same structure. Moreover, you can produce tons of results depending on how basically you define this, the isomorphism mapping. So in this case, we have identified two different matches. We have a no match of a node because of a different label. But we can also have a no match of a node because this blue node here is a bit farther away. But is that node not important at all? So it might be that actually the user here has intended something, okay, the Chicago is in the United States. But in your knowledge graph, you find that Chicago is actually in the Illinois state, which is in the United States, which is actually the case of this. So do we really dismiss that information? Maybe not. Sometimes yes, sometimes not. There is no precise answer here. Okay. So the first thing is strong simulation. Simulation comes from concurrency theory, and it is deemed to match processes. So a process is similar to another process if the set of actions are similar. So in this case, the red node might be matched to both red nodes here, because actually they all come, so they are all connected to the orange node. Okay? So simulation does this. Basically moves apart from the fact that we need a bijection, a precise bijection as in the isomorphism, and they relax saying we have a relation. Okay, so this is the definition. I will not go too much into details, but it's basically saying that basically if a node belongs to the relation, then also the fathers, so the parents of this node, and also the children belongs to the relations. So it means that basically the same labels that you find in the parents, you also find, so the labels that you find in the parents should be part of these relations. This is actually particular, it's called duality, this property here. And in the simple simulation, you have just the relation with the children. This is the dual simulation version. And the strong simulation enforces a third part, which is locality. Locality means that you don't want to match things that are around in the graph. You want to match only things that are connected together. And second, you want to bound the things. Because since you are talking about relations, if you have a sequence of nodes with the same label that then is, for instance, orange, and then is connected to a red node, basically the simulation approach will just collapse all the orange nodes in one single hypernode somehow. That's the problem of normal simulation, but it is bounded by strong simulation. Okay, strong simulation is actually very good. So it's polynomial in time, and it's more expressive than dual simulation and the graph simulation. As I said, you have seen from the definition that they include these definitions. So it's pretty clear. Okay, let us move apart from this and to a work which is called NEMA. NEMA is basically a work that tried to match approximate structures, but trying to preserve somehow the fact that two nodes that are connected in the query should be also, sorry, two nodes that are close in the query should also be close in the graph. So these red and blue nodes should also be close in the graph in order to be matched. Okay, so the structure is not fixed anymore, but so it can be, so that the best match in case of NEMA is the subgraph isomorphism. But actually, you can have flexible versions. So you can have flexibility because you don't require anymore to have the objectives of subgraph isomorphism. So the idea here is to exploit neighborhood. I'm sorry I have to go faster because otherwise we will not end up. So exploit neighborhood means that basically for each node you compute a neighborhood vector that include the nodes that are connected to a particular node at some distance. So if, for instance, if you say that the maximum distance is 2, you consider the node B, C, D, and E if you are computing the neighborhood for A. And for each of them, you give a score that depends on the distance. And it basically have an exponential decay over the distance. So NEMA is basically just doing this. It's just computing for each node in the query the best feature, the best mapping of the nodes in the graph. And the best mapping is the one that minimizes the cost. And the cost is given, for instance, if I match two labels. So imagine that matching labels in a knowledge graph is like saying, okay, I use string similarity. If these two nodes have the exact same labels, then the cost is 0. Otherwise, it depends on the distance. For instance, the Levenstein distance or any string distance, edit distance. But might be also semantic distances or other things. And the other thing is the difference among the vectors. So it's the positive difference among the vectors of the nodes in the query and the nodes in the graph. So you want to find the match that minimizes the overall cost for each node in the query, which is a problem which is NP hard, because actually if the cost is 0 is nothing but isomorphism. So the cost is 0 when, so if you have a perfect subgraph isomorphism, the cost is 0. So therefore the problem cannot be easier than normal subgraph isomorphism. Okay. It has been solved, so since it is also approximated hard, it has been solved with the propagation approach, label propagation approach like belief propagation. But you can look at in details in the paper. SLQ is actually, has already been presented in the tutorial before. It's a similar approach. But instead of having one single match, basically you have a set of transformations from the node in the query to the node in the graphs. So for instance, you can have label similarities, one kind of transformations. Can be semantic transformation from country to nation. But you can also have pathwise transformation in which you map single edges with an entire path here. And you can define your own set of transformations. So this is not bounded. The idea here was, okay, for each vertex v in the query, we find somehow we have a score, and this score is computed in a machine learning way. So basically, every transformation has a weight. So if for moving from this node to this node, you require 2 different transformations, then you will have a score that depends also on the weights for each transformation. So the idea here is basically that you learn, you also have edge transformation, you learn a model that basically says what is the probability of finding some kind of match given the query. So what is the probability that given the query Q, the match phi, which is the function that maps nodes to nodes, is what is the probability that this happens, basically. The idea is, okay, how can I learn these parameters? But they have proposed method to do this. Okay, let me move to the second topic, which is query by example. So in query by example, we actually know from database that query by example is a very, very old thing in which we have a template. So as I said before, an example is just one result of what you want to obtain. So the solution is actually to say, okay, if I match that query, which is not anymore something that I want to find in the graph, but it's an example of what I want, and I match this query here, I can find somehow other structures that are similar enough to the structure that I provided. So there are a couple of work in this area. One is exemplar queries, and the other is GQB. It's not approximate queries. So I want to stress the fact that in approximate queries, you want to find things that are as close as possible to what you provide. So the idea is that the user has the specification in mind, but it makes some mistakes. In case of a query by example or exemplar queries or graph query by example, the user just provides you an example. The rest is your work. This is an amazing area also of research right now. So exemplar queries is just this. So the user provides this example. You match this example in the graph. And I can show you with the, actually it's better if I show you this picture. So, well, what can you do here? Okay, so the user has an example, wants to know about companies that IT companies or big IT companies that acquired other companies, and wants to know about where this company, so this big company, has been founded. Okay, so he knows pretty much about Google, but this is just one. So Google has acquired YouTube and has been founded in Menlo Park. So the first step is just to match that query with some traditional techniques. You can even, the query can even be formulated in a keyword queries. We don't care much. But in the end of the day, you are interested of this structure S, which is called the sample. Is an excerpt of the graph. So it's a substructure of the graph. What you do is basically that at this point, you define a similarity relation, and you find other structures that are similar to the one that the user provided. What are these similarity things? Well, can be strict, so it can be subgraph isomorphism again. Can be approximate isomorphism. Can be simulation. So you can really plug whatever you want in this framework, and the rest remains the same. Okay. Well, depending on what is the choice of your similarity function, of course the problem might be easier from the computational point of view, or might be harder. So in this paper, so in the exemplar query paper, they have proposed a method that is based still on the neighborhood of a node. So for each node, you represent the neighborhood of a node, and then you basically, instead of matching the entire graph, you use these pre-computed tables or vectors in order to speed up the computation. So of course, you can also construct indexes on top of this. You can do a lot of different things. So, however, if you want to rank also the results, this structural information that can give you somehow, well, if you compare vectors, you can use, for instance, cosine similarity just to say this structure is similar to the other structure. But another approach is to use random walks approaches, in which you basically have, so you explore, starting from the sample, you explore a portion of the space using the random walker property. Okay, so in the end, this work was basically just collapsing all the results. So we're actually ranking all the results using these two different rankings. So the first is the structural, and the second is the random walk approach. JQB is a bit more flexible. So in JQB, you don't require that the user specifies a structure. So they actually says, okay, why having a structure if you can find it? So they said, okay, we use just tuple. So instead of providing a fully connected structure, I provide the tuple Google and San Mateo. And I'm interested in other companies and where they are based, basically, in which county they are based. And so the tuples are matched, and you find these results in the graph. How do they do that? Well, that's interesting, because what they have to do is somehow to implicitly move again to subgraph isomorphism. But in doing that, they basically, okay, first match the tuples in the graph, and then finding out a structure that has enough information or has enough value. So the idea is that they construct what is the maximum query graph, which is a graph that has the maximum weights among the edges. So in order to bound the computation, they say, I'm not exploring the entire graph. I will explore the graph. So starting from the query nodes, I will explore up to some distance, again, some neighborhood. So all these techniques use the concept of neighborhood. And then I can find the results and rank them, because again, I have weights on edges, and so I know which of the answers are the best ones. Okay, so this is the entire method. They also have extended this method to multiple tuples. What they did, in a very few words, is basically that instead of, so they find a query graph for each of the tuples, and then they basically connect all of them together. They compute what is called the union graph, and then they go again in the graph and finding the answers. Okay, this is now the turn of the second part of the tutorial.
So thanks, David. And as promised before, we will try to bridge out to the data mining community now, right? So we heard this is also an important topic in data mining, machine learning in general, but we, with our tutorial, we don't want to give you a complete overview on the machine learning topic, but more on the user perspective of it. So that's why we called it focused graph mining. So it can be used in very many domains, like link prediction, community detection, anomaly detection, you name it. Please take your example of graph mining and try to find out if there is really a user involved in your example or not, or how we can now involve the user to make it a better experience from the graph exploration perspective, maybe. So let me give you one example why focused graph mining is important. So we consider the user interest as the major tool for adaptive graph mining. But what are other people doing so far? So in current literature, you find graph analysis tools like modularity-based clustering. But these tools, they define a specific quality function. And the quality function, like modularity, has nothing to do with the user interest, right? It's a pure function that partitions your graph according to a quality measure. Now, our aim is now to introduce to this quality measure some user interest and to incorporate the user into the loop of these graph mining methods. So the main questions that we pose to the graph mining community in general are, where is the user interest in such current definitions? How can we include the user into the loop? And how do we need to change the algorithmic search? Because we could now introduce into modularity a user preference. But what changes then in the search, in the partitioning of the graph? That might be more important there. So let's see. As David mentioned before, we cannot give you all the details, but we have now one slide each for each of these methods, and you find on our website a longer version of this tutorial where you have then additional slides for each of these methods. So take it more as the overview or the teaser talk to get into this field. So one of the first methods defining focus in the graph mining community was this one by Hang Tong and Christos Faloutsos, which searches for centerpiece nodes, they called it. So there, the idea is the user provides you some interesting nodes the user is interested in. And then the algorithm finds out the centerpiece node that has direct or indirect connections to all or most of these nodes that the user provided. So here the user in the loop is the given set of interesting nodes that the user provided. And if you imagine now, this has nothing to do with clustering nodes, right? So that you cannot apply traditional graph mining technology on that. Or you cannot use shortest path algorithms because there is a specific set of interesting nodes that you have to get into your algorithm. Or also other graph mining methods lack such kind of user input. Now, as I said, in this short version, we don't have any details, but you can imagine, for example, with random walks with restart, how you can implement such a solution. Like taking the set of queries that you get and then start random walks from these nodes and measure the probability for the other nodes that you find from these random walks, and then the nodes with the highest probabilities are these centerpiece nodes. Sounds easy, but there are very many papers on that domain, so look them up. This is one starter for that direction. Another possible way to define focus is based on focused communities. So here one example which takes also internally the definition of clustering. So internally means here dense subgraphs like modularity or conductance, and introduces user preference in there. And the user preference again is modeled as a set of, they call it seed nodes. And now you don't partition the entire graph based on modularity or conductance, but you partition locally, starting from these seed nodes with local graph clustering algorithms like PageRank nibbles or other methods, and they introduce this property here to find local community detection by seed set expansion. Again, here some new research questions. Here you do not aim at a global search anymore. Independently how big your graph is, you consider the user interest to be more important, and you start from the user interest. So in this case, you might become even more efficient with your search because you focus really on the only important parts of the graph that the user thinks is important. And communities may be overlapping because of different user interests. You will find out various communities that are highly overlapping to each other. Third point for focus is a more egoistic point of view. So everyone is in the middle of the network, so everyone here in this room has his own viewpoint or her own viewpoint. And this is modeled by the so-called ego nets. So starting from one node, what are actually the neighbors of this node and the neighbors of the neighbors? And consider this as the network from which we can derive then new information. And this is only one ego net from this one node, but what you can do if you have multiple nodes from which you start an ego net perspective, you can more or less create new features for your graph mining approaches. And in this paper from VLEB 2015, the authors have done this for link prediction. So look at this figure here with two ego nets, and you can now measure the probability of seeing an edge between these two nodes based on a new feature set. And the feature set is derived by feature extraction from the ego net analysis. And here again, you as the user can define which are the most interesting parts of the graph where you start your ego nets from, and maybe use that for a more focused analysis on your graph. And now another perspective is more heterogeneous networks. So imagine you don't have only the nodes and the edges, but you have also additional attributes, like in a social network, something like age or other properties. So there has been this famous property like homophily that we know from attributed graphs, and most algorithms in graph mining assume simply homophily. They say, okay, we have a correlation between the graph structure and the node properties. Looking at my picture here, young people have a community, middle-aged people have their own community, old people in red have their own community. But this might be true for age, but for other properties it's not true, and Newman called that dissociative mixing. And now the question is, how can you actually derive new information from this homophily or dissociative mixing properties? And this is something you can study from different views on the network. So here, one example, a small network on the right, and if I focus now, as my own user preference, I focus now on income, I see two communities in the lower part and the upper part. Like the lower part is low income people, the upper part is high income people, and suddenly I realize that in the upper part with a high income, there is some deviating outlier in the middle which has very low income and seems to be a little bit suspicious in this group of people. And then you suddenly realize that based on your preference, you might have a completely different solution than other people looking at age and number of children in the same network. They have a different preference and different user interest. And now the question here is, how can you use this user preference? Or if the user, as David mentioned before, doesn't even know what the preference is, how can you learn the user preference? And that's what we do in different domains. So you could start doing this locally on very small graphs, as here on the left-hand side. For example, you might find in a small network with 3 nodes here that age is very important in this network. Or with the blue network, you find that income and number of children is important. Or if you go to the right-hand side, you have more global perspective, and just like Newman, want to know what is highly correlated to your graph structure, and you might find out that in general, age and number of children is correlated to your graph structure. So one technique that I want to show you in here is the idea of local context selection, which fits to the left-hand side that I showed you before. So imagine we want to really find out local substructures like frequent subgraphs or other local structures. And then we want to find out for these, what is the local relevant attributes. With this, you have simply to measure the dependency between your attributes and the local graph structures. And this is one example where you can use that for anomaly detection in these local graph structures. Another example, which takes a more global view, is measuring statistically the dependence between the attributes and your entire graph structure. And this is the only technical part that I want to show you here. It's more a statistical test, which is very, very simple, taking into account that high correlation between attributes and node structure means that we have more edges, right? And here in this example, we take an attribute which doesn't show a high correlation, like shoe size, and we take, for example, the range of shoe size 8 to 9, and we only look at the number of edges which is induced in this interval. And we see in our social network on the right-hand side that there is a very small number of edges in there. This makes us a little bit suspicious and said, okay, then shoe size is obviously not correlated to our graph structure. What if we take age and income here? So again, an interval on age, an interval on income, and we see some nice community forming in this interval. So what does it mean? We see now a higher number of edges. High number means here more edges than we expect from a ground model, for example, with random edge probabilities on all the edges here. With such a method, you now can infer what are the correlated properties, what are the correlated attributes. But as I promised you in the beginning, it's not the user preference still, right? So it's only one way to extract relevant information. And if you can combine that with the user preference, even better. And this is what we call focused community analysis here. It's you give me some nodes that you're interested in. So let's take our network here with the red persons marked by the user. And now we infer your preference. You don't have to specify why you like these 3 people or why you want to see results based on these 3 people. We infer from these 3 people your properties, and we do that by attribute weighting. And this is what we call focused clustering and focused outlier detection on attributed graphs. So in the first step, we infer similarity. Basically, we do a metric learning approach there. And then in the second part, we reweight the graph based on this similarity. And in the last part, we can do community or anomaly detection based on that. So with this, you can span from the user preference given up to inferring properties that the user doesn't know in one approach. And now, as a final slide, let me show you what we achieve with this in a very practical manner. Here on this slide, you see on the left-hand side what sociologists do at the moment when they perform analysis in a social network. So a sociologist has some hypothesis. And then if a sociologist has a hypothesis, then she or he goes to a kindergarten and tests this hypothesis with real humans, with children. Now, this is hypothesis testing. What you can do with the approaches that we just showed you here is more the other side on the right. You take the entire network and then you try to find out new hypotheses which are not even known by the sociologists. And in some of these cases that I showed you in the publication, you find examples like that where you can derive new hypotheses that a human being could never find by himself or herself. So thanks for this part, and then I hand over again to David that finalizes the tutorial with the last part.
Okay, so we hope that we thrilled you a bit with this kind of techniques and with this broad overview. As Emmanuel said, it's mostly like a teaser because we don't have time to go deeply into details. Otherwise, we have to skip a lot of techniques. But instead, we would like to give you this broad overview in which you can somehow dig into. You can find the publications, but you can also find the extended version that have some more slides for each of the techniques. So the last part of this taxonomy, what we call the graph exploration taxonomy, is about the refinement. And the refinement might be intended as many different things, as we said before. So the first thing is really proper formulation or refinement. When the user starts and gives you a query, so as a database person, you receive this query and you see, okay, there are many different results. And these results might be irrelevant because the user was really imprecise. And so how can I guide the users towards the proper results? So the first thing that, and traditionally speaking in all the database community, they have started studying refinement of queries. Let us change a bit the query. So if you search for something like, I don't know, you search again for the President Donald Trump, it might be that you will find some specific topic over Donald Trump. So it will be proposed that or you search for Donald in general, do you mean Donald Trump or do you mean Donald Duck? So this is, was it Donald Duck? I'm not sure now. So the idea is actually that you can change the query, but how you change the query in a graph? Well, that's an interesting question. The other perspective is the top K results. So when you, the user, yes, gives you the query, but then you realize that the results might be ranked somehow. Some of them are more important for him, or some of them are just simply redundant. So can we summarize the results? So the top K results have been studied, of course, for approximate queries, but also in terms of summarization of the results. And the third one is skyline queries. Skyline queries, as I said, well, actually there is not much in skyline queries over graphs. So, well, it might be actually an interesting directions where to work, or it might be because it is too hard, but actually, if you search for skyline queries in graphs, there is not much. And I think it's actually an interesting perspective. However, it is not in the tutorial. The only things that we have found so far are in the other tutorial, in the extended version. You will find there, but I will not present it today. Okay, so what is the reformulation, the refinement? As I already said, well, you look into the graph, in your graph, and you find way of changing the query. So usually there are 2/3 different perspectives. First is the user is too restrictive, so 0 results. If the user is too restrictive, that query is too much, so you have to remove some information. If the user is too generic, that query means that has to be changed in a way that you have to add more information in the query, more conditions. Think about SQL queries. If you have a conjunctive query, you basically add another conjunction or such thing. Another slightly different perspective for which there is even not much there is why not queries. Why not queries are when you basically have a search for something and the user will ask, yeah, why this result is not present in the result set? Why not? And it has been studied in normal databases, and there is a couple of papers also in graphs, actually. So, okay, the solution is we change the query. In the end, we find out something so we change the query in such a way that we can guide the user. An interesting perspective here is that actually, if you guide the user, why not have proper interactivity? Right now, there is no method that studies immediately interactivity. Yes, there are the HCI methods. People have understood this, but is there a proper model that actually can learn immediately from the user? This is an interesting thing that we should study, probably. Okay, so let's see what's going on. Well, this is one work. Actually, the other work that I was not aware was the one presented in the previous tutorial. That's interesting, but it's you see that it's very similar to what presented before. But okay, so you have a query and you have a set of results. The query is a structure and you search that structure in your graph database. So what is a refinement of this query is a superstructure of this query, so you add extra edges to that query, such that there exists at least one result that contains that specific structure. Well, even in this small, very, very small example, if you try to find out all the possible reformulations, here you have immediately an exponential explosion, immediately. So this is not what you want to do. So if the user has 500 results and then you return 5,000 reformulations, well, it might be disappointed again. So what can we do? We actually ask ourselves, can we find k-meaningful reformulations such that basically if I take the union of the results of these reformulations, we cover all of them, we cover all the original results, so we preserve the information or almost all the information that the user wanted. And second, we would like to show interesting reformulations, things that explain better the results, so that are different among them. So what this paper came up, so it was basically an idea to quantify two very simple measures. The first measure is coverage. Coverage is basically how many results a set of reformulations covers. Second is diversity. How many new results, how many non-overlapping results actually a set of reformulations get. And that's it. So after that, you just need to put this into an objective function, and you say, okay, I maximize coverage and some parameter, diversity, for instance, linear combination of them. I don't have the objective function here, but you can imagine that you just sum up these two members. So the second part is just for a pairs of reformulation. You have to do for all the possible pairs. So you have to sum all the possible pairs, but you basically obtain your objective function. And this problem is basically a variation of the maximum coverage problem, so you need to somehow rework a bit the algorithm. So another work which has not many insights, but it's actually interesting. Studied why empty, why so many answers. And so in which you have a query over a graph, in this case, not a graph database, and for which query you have too many results. So, or you have a query for which you don't have any results, so it's empty. So can we somehow change this? So their focus in that work was basically to provide explanation. Another word that I would like to tell you is explanation. Sometimes we need to explain to the user why such a result is returned, why such a formulation is performed. So the user is sometimes lost, but it is lost because the system doesn't provide any information more. So in this case, they studied a very simple things. Okay, you have exponential number of variations if you just change the query. Okay, you can compute them because the query is usually not so big, but still, you can do something better. So you find the maximum common subgraph. So assuming that for each of the results that you have, you find that that structure, or better, this is an empty query. So if you don't have enough results, you look around and you find the maximum, the biggest subgraph such that you obtain some results. And then you have the differential graphs that basically gives you somehow the explanation that this part here is the part that if you put in the query will destroy your result set. And this can be used as an explanation. Or you can perform modifications of the query in order to have results. So you just change the results. And this is mostly a query-based approach in which you thrill the user with more results. You want to find out some results from the empty answer. So another work was instead finding the top K queries. As I said before, top K is a different perspective, but in this case, it was, okay, I have a query. Let me go quickly to how the query is done. So you represent each graph as a set of features, where a set of features might be small structures. So you extract frequent patterns, and every graph has basically a set of these frequent patterns. And the query is a query over a vector now. So the query is that specific function here that takes a vector graph and returns -1 if the result is not relevant and 1 if it is relevant. So it basically shows you in the set of graphs which are relevant and which not. The idea here is, okay, once we have all the results, can we somehow find K results that summarize all of them? The idea was, okay, well, we can think to graphs in a multidimensional space. Or actually, we cannot, even can move a part of this, but just saying, okay, I compute a distance between a graph and the other graphs. In this way, I can take each graph and construct a neighborhood, which is not the neighborhood that I presented before, is the set of graphs that are at most distance d, basically. Where the distance in this case might be, for instance, the graph edit distance. In this work, it was graph edit distance, actually. So they say, okay, if two graphs like those ones are in the same neighborhood, they are redundant because they are very, very similar. Why should I return both? So the purpose of that work was to basically finding K representative queries, so finding a set of results such that they represent all the other results. And this can be achieved by considering this neighborhood that I already said, and somehow a notion of coverage. So how many results from the query this set of results S covers? How many results from the query? So the red dots are basically the results of the query. So this is the results that we are interested in. And we try to find these that are as far as possible together in order to cover all the space of results. Okay.
Are you sure that is it assumed that the result sets are distinct and we have to cover like distinct sets?
Well, it was a maximum coverage approach basically, but in fact they don't actually put any diversity inside, so they don't say explicitly that they are distinct, the two things. So they say that they can achieve this, but it's not explicitly in their it's not explicit in their formulation actually. So they say that the representative power, so they want somehow to maximize how many results I cover just by looking at the neighborhood of one specific result. Okay. Another way of summarizing results, maybe I have to go a bit quicker here, but it was this. So given a keyword query over a graph, we can find a lot of answer to this keyword query over the graph. And the answers are represented as subgraphs. So we would like to find somehow over all the possible answers a summary. And this summary should present the connections, the pairwise connections among the nodes in the query. So it means that basically you want to find a compressed graph that represents that specific answers on the left. And this can be done somehow with this proper formulation. So it's among all the possible pairs of query nodes that I have, how many of them are actually preserve the connections. So in this case, in order to go to C, we have to go to an intermediate node, and this is always true. To go to B, we have to go through two intermediate nodes, and this is true. This is what they call the one summary. So if you want the complete information, you have to have a bigger summary, basically, because you want to preserve all the possible connections among the pairs. But they have also a relaxed version in which you have partial summaries that they might not preserve the pairwise connections among the nodes. Of course, actually, they have proved that this problem is easier than all these other problems. And this is because this is somehow based on a dominance relation, so how many things we can cover. Okay, the last thing is about top K results, and it's a work of Wenfei Fan. And the idea here again was, okay, given a reference node, so we are interested, for instance, in finding good project managers that connect to a database person and a project graphic graphic system. Basically, how can I find good project managers? And good project managers are those that are somehow well connected in terms of connections of the underlying parts. So these people here. Instead of using subgraph isomorphism, they use a simulation approach in which they, as I already presented, basically multiple nodes can end up in the same simulation, in the same simulation relation. Okay. Here again, they have a diversified approach, and they have two different measures: relevance and diversity. Relevance is how many nodes I can reach. So this project manager can reach, preserving this, not structure, but this this simulation basically. So if I simulate these structures in here, I obtain this. So the reachability, these factors quantifies how many nodes I can reach from the output node. And the diversity shows, okay, if you return multiple of these project managers, how many common nodes are reached. And they want to maximize both. And this is their objective function. Okay. I will skip this part because we are almost out of time. And let's go on the challenges that I think are interesting for this tutorial. Okay, let me recap a bit what we have presented so far. So, what is exploratory graph analysis? Well, we intended for exploratory graph analysis two different things. The first was approximate queries, in which basically a structure which is not fully specified by the user can be matched into the graph. And second, we talked about by example methods. The user provides an example of the results that he wants or she wants. So why this is important? Well, we need only partial knowledge. So the user here is guided by the system. The system is flexible enough. Or the system is able to understand that this is an example. And this example can be found in the database and then matched against other things. We actually thought about challenges. And we found that there are several challenges. These queries are not supported in any graph database. Well, one thing that you can think of, well, they don't scale too much, so we need somehow to standardize these procedures. But there is no universal index. So for any kind of query, and you realize because we are all database researchers, for any kind of queries, basically we need to construct a proper index for that query. And well, it hasn't been studied any partitioning method that preserve the query properties or these query properties. So for other queries, yes, but for approximate matching and for by example methods, we don't know. From the data mining perspective, well, I talked about interactivity, but these methods are not really interactive. So this method might be interactive. So if you keep reformulating or refining these queries, or you just see that you have an approximate queries and then you basically return other results and you cluster them together, but they are not interactive at all. There is no solution if you have probabilities on the graphs. Might it be also interesting? If you have dynamic graphs, for instance, so if the graphs evolve over time, do you have to change completely the underlying structures? And if you have an index, does this index adapt to the dynamic graph setting? And the same is also for streaming settings. One thing that we can do from the information retrieval perspective is to exploit query logs, or also instead of or enriching the information. So if the information in the graph is too poor to explain something, why not we go to other data sources? Why not going and searching other data sources, exploiting the graph structure first? So this, I rarely have seen these kind of things, and I think they are very important perspectives. So the summary.
Yeah, maybe for the graph mining, I think we have structured it in different perspectives. Like at the moment, you can model user interest by a query, giving the query to the graph mining system. Or as seed nodes, we have seen several methods that base on this paradigm of seed nodes. Or by weighting attributes. But is this all, or can we find out more? And I think we agree at the moment that this inferring the user interest might be the most promising idea. Our users, at least at the moment, are not aware what they are interested in. So how can we help them in specifying their own user interest? Interactivity is a must-have, right? We cannot live with all these parameters of these methods that we have at the moment. How can we intuitively parameterize? And adaptivity, as David said before, has to go into graph mining, and we have to find a way to do individual, more or less local search in the graph and not global search as we do it at the moment. And as a summary for that, we try to follow the same structure as before. User interactivity as one major challenge. In most graph mining algorithms, it's unsupported, but even if we support it, how can we support it? Is there a way to have this variety of user interactions in the graph mining method itself? Or how can we unify it and make it exchangeable, the user feedback, to other methods? More or less, it will be a revolution in the formalization of graph mining methods. So imagine you take one graph mining method and you want to make it user aware or user interactive. Then it's great, right? We can publish all our old graph mining methods anew with an interactive scheme, but that's not really the purpose of science, right? So we want to have more a flexible scheme that we can cope with many different graph mining approaches and more or less be adaptive and steering our algorithms towards the interest and formalize, specify the user interest in a general way. The last bullet point here is, I think, the most important one. At the moment, most of the graph mining methods is evaluated on some data, but with no user at all, right? It costs, as we heard this morning as well, the user queries cost us a lot. And that's why we as scientists, we don't care so much about the user interest, because we would need to perform a user study. And we don't have time for it. But in all these cases, you need user studies, and we shouldn't accept papers without user studies if we claim user interactivity in the paper. The last point is obvious: scalability of our algorithms. Most of these problems that we proposed here are NP-hard problems. Still, they are not scalable. Even if we go for heuristic approaches to large graphs, they don't scale so far. We have to exploit the user interest in also pruning our search space. The user helps us also in the scalability issue. So that's it for the graph mining approaches. And one final slide.
So this part that relates on the refinement of query results, it's also very interesting. So we have seen that it's not easy to find proper refinements. But again, the finding refinements or changing the query or returning top K queries is important. But one of the things that are definitely missing from the user perspective is that we never actually keep going in drilling down with the user preferences. So I think that actually one topic that anyone can work on is basically to try to have proper interaction with the user. So the user provides you feedback on the database basis. So why not exploiting this feedback? I think it's amazing. Of course, it's not easy. It's not easy at all, but we can actually bridge the gap that there is from machine learning to here. And the idea is that here, another thing that I currently saw that was missing was basically that database don't implement any reformulation. There is no reformulation. There are ways of querying your data, but not how to change the query. So you have to send yet another query, and yet another query, and query, and query. So probably it's time to start thinking about systems that embed this functionality inside. And another thing that I also mentioned before was explainability. Why do we return results? Why this result is important? So we have somehow to let the user explain why he wants some results, but also let the machine explain why it returns some results. So we are very good in programming or in creating algorithms, but these algorithms are never explained to the user. So we return such result because 70% of the other results are similar. This is an explanation, but it's never provided. And the user is unaware of what the system is doing. And if the system doesn't adapt, and it's just detached by the user, well, we don't have any chance to communicate with the user. And so, well, I put other perspectives here. Faceted search. We heard this morning about faceted search. This is another interesting thing. So while we are exploring the graph, can we also showing different topics at the same time? And in this topic, just let the user choose what is best for him? Well, of course, from the scalability point of view, again, real time is actually not true. So try any of these algorithms. They scale, yes, with the huge assumptions, but in any other case, they don't scale. So probably we have to rethink also every partitioning method, as I said before, should be rethought in this way. And of course, the learning of user preferences. Okay, so the last slide is basically this, is our vision. We probably need to talk about missing tiles. We need to talk about interactivity. We need to embed interactivity in our system. We need to have adaptive systems. So indexes shouldn't be fixed indexes. Why we have studied adaptive indexes for relational databases or for textual databases, but we haven't studied the adaptive indexes for graph databases, or very few actually of them, very, very few. Personalization is also another issue. Sometimes you might argue that personalization is a bit too much. So if you personalize the results, then you basically can just steer the user towards always the same results. Yeah, well, it's another discussion here. And scalability, of course. Okay, this ends up, and I think I will end with this slide, which is more. So if you have any question or suggestion?
You mentioned that some version of the tutorial or part of
You mentioned that some version of this tutorial or part of it is on your website with additional content. So if you could put up a URL of that, maybe?
Yeah, if you search for HPI graph exploration tutorial, you will find the original version. Okay, and if you go in that page, I think it also references the original slides, so the extended version of the slides. And there you will find some more details in the techniques. So we are sorry that we cannot present in detail. Of course, we have them, but going into details requires a lot of time.
But maybe you also have other suggestions like what we missed. So
Yeah.
it's only our vision that we presented in the last few slides, what the challenges are. So David finished with the very last slide on the personalization and adaptivity. Any other ideas? What is missing in the area?
I'd like to share one of the problems I once came across, which is definitely goes under these birds, like graph exploration. And I think it was an event dedicated to data analysis organized by the Transport of London. And there was a problem about finding correlations between road closure and traffic jams. And they had data about road closures. So they had, of course, the graph of the roads, and they also had some data about the speed on the different segments of the road network, but it was extremely difficult to write any meaningful queries, and I didn't succeed. So can you suggest how some methods for dealing with this problem?
So basically the question was about these road networks that have some, so these huge road networks with traffic as well, right? Well, so the techniques that we have presented today are general enough to cope with this. Of course, queries with road networks are a bit different from the queries we have presented that are mostly structural. But for instance, you can use focused graph mining. So you have some point of interest, and you select this point of interest, but you don't know which characteristics of this point of interest you like, and you don't want to describe these characteristics. So you have 2 or 3 of these point of interests, and basically then you can somehow find routes or best routes that connects this, or that shows you parts of the city that are actually have other points that you like. Or for instance, you're interested in museums and you go for routes that go for museums or things like this. There are also some works in multimedia analysis that have done such thing, like the beauty of a path, for instance, that is also related to the users. How beautiful is a path? So how can you quantify beauty of a path instead of just going for the shortest path? But yeah, sorry.
Okay. Well, first, thanks for the tutorial. I found it really interesting, and in an area that I'm not aware of the literature, you did a great job in trying to summarize so many papers. One of my thoughts when dealing with this problem with students, or when I work with people to try to begin any data analysis process in which we use graphs, is that we tend to assume that graphs already exist and they are the initial point, and we do all of our analysis with that. But my feeling many times when you have data sets, well, you could say social data sets which are complex with different types of information that we need to combine, we need to decide what is our mapping from that sort of data to those relationships. And do you have any ideas in whether there could be processes like those ones in which, rather than adapting our queries, maybe we actually adapt our idea of the graph that we are creating so that it can be useful for the users and not?
Oh, well, this is a nice question actually. So adapting, we haven't actually went into that part in which the graph changes as well. I think there are some works that take into account also how to integrate different data sources or different things into the, as the user demands for something. So if you search for some specific node, this was, for instance, you are searching for a user and that is interested in some specific shoes or something, and then going inside Amazon and finding out about shoes and things like this. I haven't seen anything so far about this. So this is what I also said in one of the previous techniques, that they don't consider other sources. So we tend to have that vision exactly, to have the static version of the graph, and then we perform analysis of the graph. But I think
another interpretation to your question could be also if we really need the graph, or which data sources are a graph and which not. And some revolutionary idea would be skip the entire graph and go for vector spaces, or encode everything into the graph. Both are maybe extreme points of view, but at the moment the literature is doing that, right? So either you are a fan of a graph theory, and then you model everything in your graph, even male and female are nodes in the graph, or you go and convert the graph structure. Both is possible, but I think in our tutorial we try to keep the natural data as it is and then try to cope with it. That's why some of these complicated ideas have specialized solutions, because they have really a heterogeneous network then. Maybe one final question.
Thanks for the Thanks for the nice tutorial. In your graph exploration, the part at the beginning, I didn't see comments related to graph summarization. Summarizing large graphs into, supernodes. It's been done in biological networks as well.
Yeah.
So what is your comment on that? Is it considered part of your exploration?
Yes, it is. It's a very, very nice question. Actually, yeah, it is. We didn't consider this here because actually we haven't seen any kind of personalizations so they have been used for reducing the size of the graph and having a compact representation for preserving some kind of queries. But basically, when we did this tutorial, actually we never thought about summarization. But then talking with other people, they actually made the same comment and say, okay, yes, we can actually see summarization. And there are a number of works either preserving most of the structure or preserving some patterns in the structure. So there is a lot of things. But also the space here was limited. So, but it's really interesting. Yeah, thank you for the question.
Maybe in the same line of thought, also skyline queries and the whole optimization theory behind that was also skipped from that for the short version of the tutorial. Might be also important to see how this evolves for graph analytics.
But there was also a tutorial on graph summarization explicitly. I think ICDM 2015 from Danai Kutra and all these groups of people that actually studied heavily summarization. That's why we actually thought not to put inside this tutorial. But it's definitely related, so yeah, it's definitely something that we can do.
So thanks again. Enjoy lunch.
Thanks.